Good afternoon, everybody. Today's topic is about doing CPU Hotplug in QEMU. My name is Bharata. I work for IBM's Linux Technology Center from Bangalore, India. There are other two co-authors for this work. One of them is right here, David Gibson. Do you want to introduce yourself? Or?
Sure. I work for Red Hat remotely from Australia, and I've been working on QEMU for quite a while. I used to work for IBM where I also worked on QEMU, so there you go.
Yeah, so the third co-author in this work is Igor Mamedov, who works for Red Hat from Czech Republic. Igor has been working extensively on the Hotplug infrastructure, memory, and CPU Hotplug on x86. So in today's presentation, we will look at the new way to do CPU Hotplug in QEMU, mostly for a couple of architectures, x86 and PowerPC P series. We will look at some of the challenges we have had and some of the solutions we have worked out towards solving them. Finally, we will end the presentation by looking bits and pieces of future work that we have lined up in the area that is related to CPU Hotplug in QEMU. With that said, let me get started with the actual presentation. Yeah, so this is kind of mandatory introduction slide we kind of retained here just for offline reference, but since it is here, let me just go through it anyway. So what is CPU Hotplug? It's about adding or removing virtual CPUs from running guest dynamically, which means that you'll be able to add or remove CPUs from the guest without ever having to reboot the guest. So that's the key point here. And as you all know, so this feature is useful to scale the guest's compute capacity on demand, which is typically useful in implementing some sort of vertical scale-up solutions in the cloud. That's about the use case part of it. And the other point I want to touch upon here is the guest awareness part of it. CPU Hotplug has been supported in Linux kernel and hence in the guest kernels for a long time now. So nothing new is needed on that front, but there is a little bit of plumbing work plumbing support. I wouldn't say work because it's already done. There is some plumbing support that is needed if you want to have CPU Hotplug running fully on architectures like PowerPC. That's because in Power we have this set of standards called PAPR, Power Architecture Platform Reference, which defines a set of standards for communication, or it defines interfaces between the platform and the OS. So it's a big set of standards. One part of it talks about dynamic reconfiguration, which defines the kind of communication that happens or supposed to happen between guest and the host when you are bringing up a CPU, a dynamic resource like CPU, and assigning it to the guest. So this part of the work is typically handled by a set of user space tools in the user space tools that we call RAS tools in P series. So the point I want to make here is if you want to have CPU Hotplug working on Power, it's important to remember that these user space tools are running inside your PowerPC guest. Yeah, so let's begin by looking at what we had prior to starting this work on CPU Hotplug. CPU Hotplug, as I said, is not something very new to QEMU also. We have had this CPU add QEMU command since long. But this command was supported on x86 only, and the other thing was it provided addition of CPUs, but there was no way to remove the CPUs. So it was plug only, but no unplug. And it was not generic enough so that it could be used easily for different architectures. the semantics of CPU add is such that it adds one CPU thread at a time, which made sense for x86 and worked for x86, but for platforms like Power, the minimum granularity of adding a CPU is a CPU core, which is a bunch of threads actually. So that wouldn't work. The semantics wouldn't just work for other platforms like PowerPC. And the other thing that I have noted down here is doing out of order CPU addition would break migration. So these were some of the limitations we had. And CPU Hotplug has had a long history of development actually. So when I first posted CPU Hotplug patches way back in September 2014, my implementation for CPU Hotplug on P-Series was actually based on CPU add command itself, where I used to add a bunch of CPU threads belonging to a core in response to one CPU add command. So right then I was told very clearly that CPU add is kind of legacy, and the right way to do things when you are looking at Hotplug is to use device add. So because device add is the standard way of adding devices these days in QEMU. And another thing was that CPU added CPUs, but there was really not a good way for a user to figure out the list of possible CPUs that could be added to the guest. And also where these CPUs would end up on the board. So these were some of the limitations that we have had with CPU add command. So that's CPU add was what we had, and we wanted something which was a bit more generic so that it could work for different architectures. And some of the requirements were pretty clear to us right up front, but many of the requirements started becoming clear as we went through, as we iterated through different implementations. Yesterday, in fact, I was going through the mail archives and counting the number of RFC posts I did towards CPU Hotplug, and it counted to 14. So it's not that I was posting the same patch set series for 14 times. And then I figured out there were 6 different implementations in this 14 patch set, 14 versions I did. So it's been like trying out a lot of different things, different semantics, and trying to come up with model that could work for most of the architectures and machine types. Again, the one thing we realized was that it's not possible to have a model which would fit in for all the architectures and machine type. But at least what we wanted was a consistent QOM COM model for CPUs. If not such a model which kind of works similarly across other architectures, if not same. So that was one of the goals. And of course, it has to be based on device add. Another requirement that was another thing that was really needed was a common way to introspect and introspect the or discover the CPUs and provide information about all possible Hotplug CPUs and the properties to the users, so that users are in a good position to figure out. When I say users, it includes management applications like libvirt. So they should be able to figure out what's the device type, what's the CPU device type that I should add, and where this CPU would actually go and fit into the board. So these are some of the things we had in mind when we set out and as we progressed implementing CPU Hotplug. One of the first questions that we have had to answer is that at what granularity would you implement CPU Hotplug, right? There are these common granularities that we are all familiar with. Should we do CPU addition or at thread granularity, or should it be done at core granularity or socket granularity? So let's look at each of these and see the tools and the advantages and disadvantages of each of these. So thread granularity x86 already supported by way of CPU add. So if we are implementing or if you are coming up with a model based on thread granularity, most of the existing guest tools and management, it would be easy on existing guest tools and management, and of course it would work for x86. And as I said, right, for platforms like P-Series, core is our granularity, and this model of adding thread by thread simply doesn't work because we have no way to actually expose the Hotplug event to the guest and at thread level. Basically, the Hotplug event is informed to the guest in terms of core. So that was out of question for us. And then what if the model implemented a CPU Hotplug at core granularity? Of course, it's perfect match for P-series or SPAPR, but there was no reason really to make this generic enough because it was not useful for other architectures. Then there is this interesting granularity called socket granularity, which is kind of artificial because the construct socket itself doesn't exist on PowerPC, and it kind of becomes artificial for us. And there were, in fact, suggestions that we should closely model CPU Hotplug in a way that it is done in physical, basically. So essentially, in the physical world, it is possible to do add or remove a socket at a time. So there were suggestions that let's do that in the virtual world too. But even that was problematic for x86 too, because x86 was already doing CPU Hotplug at thread granularity, ACPI spec, as well as guest kernel kind of handled or dealt with CPU addition at thread granularity itself. So it was even for x86, I think it was a little difficult to go with socket granularity. Yeah, so eventually what we kind of ended up with is that let's not try to have one model with one granularity and try to fit everybody into it. That would be very artificial. In fact, I had a couple of implementations where I was actually implementing CPU Hotplug for P-series in terms of sockets. So we added an artificial construct called socket that would add cores underneath. So yeah, we had all those things, but eventually we decided that it's up to the machine type to figure out what is the granularity. So x86 ended up going with thread granularity, while PowerPC stuck with the core granularity, which is much more natural for it. This choice made sense because in future we could have different configurations like multi-chip board or heterogeneous configurations, and it makes sense to leave that flexibility or have that flexibility for them to do Hotplug in whatever way they would like to do. Yeah, so let's look briefly at CPU COM model. So the vCPU thread, which eventually ends up doing KVM run IOCTL. This was already represented as a COM object for most of the architectures, I would believe. What we wanted is this a different unit called Hotpluggable CPU unit or Hotpluggable CPU module. And we wanted this too to be a COM object derived from device class, so that it becomes possible to user instantiate this Hotpluggable CPU object by means of -device or -device add command. The vCPU thread, as I said, was a COM object, but it was not user instantiable. The actual Hotpluggable unit that I'm talking about in the second bullet point here, we wanted it to be user instantiable. In some cases, like x86, where they do Hotplug at thread granularity, actually this Hotpluggable CPU module is kind of same as the vCPU thread object. So they are one and the same, as shown in the graphics on that side, where you can see that the thread CPU thread object QEMU 64-x8664_-CPU, that kind of is the CPU thread object is directly sitting on machine peripheral in the COM tree. If you compare that with what we have in P-series, where the granularity is core, we have this core object sitting on machine peripheral and then thread object sitting underneath it. So what is directly user instantiable here is core, while thread is kind of indirectly instantiated. So we talked about all these three different COM objects, right? Hotpluggable object could be thread, core, socket, of course, doesn't exist. But not all machine types need to have all of these. For example, x86 doesn't use the core object, while P-series uses it. So there are these two common options on QEMU command line, -SMP and -CPU. -SMP specifies the number of CPUs that you would boot the guest with. It also specifies the CPU topology as well as maximum hotpluggable CPUs that you could ever have with this guest. and dash CPU specifies the CPU model that the guest would have. So in the model, in the Hotplug model, what we do is that the machine type code extracts information from these two command line options and comes up with hot pluggable CPU, right number of hot pluggable CPU objects of the given CPU type. Currently, we derive the CPU type from dash CPU command line switch, but nothing prevents from having some heterogeneous configurations here too. Yeah, so x86 did not need any different or special construct as far as COM objects are concerned, but since we were doing at adding CPUs at core granularity, we needed this CPU core type as a generic type that we had to introduce so that we could inherit our model specific core types from this generic CPU core type. Yeah, right now SPAPR or P series is the only user of this generic CPU core type, but it could be used by others in future as well. So this is the example comparison of the CPU type hierarchy in x86 as well as P series with this new CPU Hotplug model. There you can see it's all threads. Here it's all cores. The bottommost part is the actual hot pluggable unit, that is the model specific CPU, which is kind of inherited from x86 64 CPU, which is again inherited from the generic CPU type. In case of power, the example is about some version of power 8E, where the core type is power 8E, and it is inherited from generic SPAPR core type, which again is inherited from the generic core type. So this is how the type hierarchy looks like in the model. So finally, this is where we ended up with this. This is the semantics to do CPU hot plug in QEMU. And this is going to be present in the upcoming 2.7 release of QEMU that is supposed to happen next week. So what we have is this CPU device type as well as some options, socket ID, core ID, thread ID specified along with the dash device command line switch. CPU device type is of course machine dependent. It varies between machines. For x86 it will be different, and power it will be different. And this combination of these three parameters or the properties determines where exactly your hot plugged CPU would sit in the board. And again, some of these are optional, as seen in the examples here. For SPAPR, only core ID is enough to actually specify where exactly that CPU would be inserted. For x86, I think all the three options would be needed. Yeah, so these are the real examples of specifying or hot adding CPUs on x86 as well as SPAPR. Yeah, so we saw how to do CPU hot plug from the monitor, but how do we know what kind of CPU objects to create? What are the properties and what are the values for these properties that we should use? There has been what we ideally, as I touched upon some time back, is we ideally need some sort of discovery and introspection to figure out what kind of CPU device to add. This has been kind of, how would I put it? There has been a lot of discussion around how do we introspect or how do we discover the CPUs and export the information to apps like libvirt. But there were even suggestions that the hot plug implementation itself should kind of have this introspection mechanism built in for CPU objects, so that probably using QEMU link properties, so that it becomes easier to just export them and provide the information to the management applications. So while we were going round and round discussing about how to do this QEMU link based introspection mechanism, in fact even had a couple of implementations to figure out how exactly it would look like. That's when I think Iger came up with this suggestion that let us disassociate the introspection part from the actual hot plug implementation part. Let's implement hot plug separately, and let's have a HMP based introspection or discovery mechanism where we will be able to export information in a uniform manner which would work for most of the architectures. So that is how this QMP command, query hot pluggable CPUs, came about. It kind of lists all the information about the existing CPUs as well as possible hot pluggable CPUs. It lists the device type information that you need to use for adding the particular CPU device, along with the properties, socket ID, core ID, etc. Yeah, and there is this HMP wrapper too for this. Yeah, I would quickly have a 2-minute demonstration of. I want to show how this really looks like on a P-series machine doing CPU hot plug. It's not kind of really exciting demo or something, but it just has that novelty part because this is the first time we are doing hot plug here. Yeah, so here am I starting SMT4 P-series guest with Power 8E CPU model specified. So the guest is supposed to come up with one core having 4 threads, and it can grow up to max CPUs, that is 8. It can grow up to 8 CPUs, which means that there is room to add one more core here. Okay, so I was kind of doing it, recording this demo from the hotel network. I think that was not the fastest of networks we have. So. Yeah, so here we have the guest booted. It's Fedora 24 running latest kernel, and it has booted with one core with four of its thread online. Let's connect to the monitor, look at all the threads, 4 threads, 1 core, and this is how the hot pluggable CPU HMP command looks like. Here we have this boot CPU listed. It lists the CPU device type that needs to be added if you want to ever hot plug it. It lists what is called QEMU path. There is a property called QEMU path, which, if populated, indicates that this CPU core is already plugged in. If it is not there, it means that it's a candidate for hot plugging. So this is the boot core which is already plugged in, and the other one which doesn't have that QEMU path is the one which can be plugged in now. Just one additional step or check in PowerPC guest, we need to ensure that the guest user space tools that I was talking about is running. Yeah, so that's how we typically add a CPU device. Specify an ID to the device and use the core ID that the QEMU command showed. There it is. So your CPU came up online. Now we have 8 CPUs, 2 cores, 4 threads each. And you can see all the 8 threads. And again, if you run hot pluggable CPUs, you would see the first core now populated. Yeah, of course, what would you do after plugging in? You just unplug and remove. So, yeah. Yeah, so okay, so the core is back in its original form. Right, so yeah, so these were some backup slides we had. Yeah, over to you, David.
Right, so I'm now going to talk about some of the problems we encountered as we tried implementing this. Start off with the easy ones and move on to some of the trickier ones we hit. So one fairly simple problem was that KVM doesn't allow you to destroy vCPUs once they're created. And to extend KVM to let you do that would be nasty. So the KVM people obviously didn't really want to do that. So what we're doing instead is when we unplug a core from the QEMU side, we destroy the QEMU representation, but we keep what we think of as a parked KVM vCPU. So the vCPU in KVM is disabled, it's not running, but it still exists as an object. It takes minimal resources, a few little kernel structures. If that core gets replugged again in future, we'll reuse and unpark it and connect it back to the QEMU CPU. So fairly straightforward, fairly obvious solution for that little problem. Next problem is a little bit more complicated, is how we deal with errors during the hot plug. And there's several places that errors can occur, or what we're also dealing with here is where the errors are due to assertions. I mean, we've got, as we've said, this scheme can theoretically allow things like heterogeneous systems, but obviously most current machine types won't allow that, shouldn't allow you to try and plug in two different types of CPU to the same board. So there's various problems that we want to check for. Now, one place that things get checked is in CPU realize, and that already uses the QEMU error infrastructure to report errors cleanly, but it's specific only to the CPU and doesn't know about the machine type, so it can't really check constraints that are imposed by the machine type. The machine has a plug handler where we can check machine type things, but by the time that's called, the CPU object already exists and it's kind of too late to roll it back if something's wrong. So that's pretty awkward. So this is another suggestion from Igor. We have added a pre-plug handler that is a bit similar to the plug handler. Any hot plug handler unit can register it, and it gets called before the object is created. So it can basically validate parameters of the object, make sure it actually fits, you know, this hot pluggable object fits in the place you're putting it, and can fail gracefully if it doesn't. So pre-plug will be called, then the object will be realized, then the plug handler will be called, which does the final work, and so forth. So that works fairly well. This CPU validation is the only thing we're using it for yet, but it could be used for other things. I'm actually going to skip this because the next one's more interesting and we don't have much time. The big problem was with CPU indexing and migration. We hit an awful lot of problems here, which we only kind of just fixed in time. So the way things worked is CPU index was used through lots of QEMU to identify which CPU thread was which, and that was allocated in CPU exec init, which is a function which has been around forever, since before QEM existed and all sorts of things. Because it was allocated there, that meant the value depended on the order in which the CPUs were instantiated. Now that didn't matter in the past because CPUs were already always instantiated from the beginning up through to the last one. But once you start adding Hotplug, obviously that's not true anymore. That was, in particular, that CPU index is used as the migration ID, and if the migration ID doesn't match on the source and the destination, then nothing works. Obviously, you can't reasonably ensure that you unplug and unplug things in exactly the right same matching order on the source and destination, so that's not really... So the upshot of this is if you plug your CPUs in any order other than 0, then 1, then 2, then things will break if you migrate afterwards. And in fact, it's already broken on x86 with CPU add if you add things in another order. People didn't notice because libvirt always plugs in 0, 1, 2, 3, and you can't unplug. But that was actually already broken. And the problem was that we obviously wanted a way to devise a stable CPU index. That was made complicated by the fact that different architectures are partially converted between different QOM models, and the time at which things were generated is very complicated. So we had to come up, particularly this is fairly late in the 2.7 cycle, we had to come up with something that wasn't too invasive to determine these. The way we've done that is that a machine type is allowed to allocate CPU index values in some machine-dependent but stable way before the CPU is realized. And that's a prerequisite for allowing CPU hotplug. If you want to allow CPU hotplug on your machine type, you must allocate CPU index values stably rather than just using the default instantiation order-based method. But that does mean that machines that don't support CPU hotplug, or like the dozens of embedded systems we model, don't need to change just yet. and can keep the new code, which means the change is a lot less invasive. So that's what we needed to do to get migration working more or less sanely. Right, so what do we still need to do? Probably the biggest thing is NUMA. So at the moment, the management tools basically need to guess what NUMA node CPUs they add will end up in. That's already a problem with CPU add. It's not necessarily obvious. They work it out by basically making assumptions about how the NUMA nodes are distributed, how the CPUs are distributed amongst the NUMA nodes, which work in practice but aren't really very well guaranteed. The NUMA command line, in fact, the entire interface in the NUMA command line is kind of broken because the CPU, it's essentially by CPU index, but CPU index isn't really supposed to be something that's exposed outside QEMU. It's not really. It's supposed to be just an internal ID. And the other problem, of course, is you can't really know about what the possible topologies are until you do the query hotpluggable CPUs, and by that time you've already issued the command line, so it's too late to change your NUMA options. A possible solution suggested by Igor is to basically as a replacement for the NUMA command option, instead you start up QEMU without any NUMA nodes assigned for the CPUs at least, and then use new QMP commands to manually assign the possible CPU, so the CPU slots, to the NUMA nodes you want, and then you actually start the thing. There might still be problems with that. It's something we're considering. We're still actively working on how to do that. We've got some ideas, but nothing's really settled yet. And it looks like we're out of time, so. Okay. Obviously, we want to support more machine types. S390 actually implemented CPU add because it did work for them, but at some point we'll want to move them to the new model. Vert is almost certain to want CPU hotplug, maybe other ARM platforms. This model should allow it. I'm not sure what the details will be. We've got in the works a model that the P-series model is specifically a guest on power. It's a paravirtualized machine type. But they're introducing a model for that implements the whole of power hardware, including the hypervisor facilities. That's more for experimentation and bring up than for production use. But that may well want to support CPU hotplug, and there it really will be a model of what the hardware physically is capable of. That's going to get complicated because there the unit of hotplug is going to be a whole chip, which includes both CPUs and host bridges and memory controllers and other stuff. So not clear quite how that'll do, but as I mentioned, stable CPU indexes are a prerequisite for implementing hotplug on a platform. They also need to make sure that the CPU exec init and exec exit functions are called realize and unrealize. A lot of platforms other than x86 and Power call them at init and finalize time, which has various problems. So there's basically a bunch of prerequisite cleanup that machine types need to do before they can implement the new hotplug model. We've got some power-specific stuff we want to do. Cleaning up how we create the device tree. This isn't device tree in the QEMU sense. This is the device tree that gets passed to the guest firmware and then through to the actual guest operating system to advertise what things are available. That represents cores, but at the moment it's generated on a thread-by-thread basis, but we turn it off for everything except thread 0 of each core. It's a bit messy. We want to clean that up. DSC state, this dynamic reconfiguration is a fancy IBM word for hotplug. It's a firmware abstraction that's used to communicate between the guest and the hypervisor about how to unplug and plug various things. At the moment, if you're in the middle of a hotplug operation and you try to migrate some state might be lost and things will go wrong. You're okay to migrate before your hot plug, you're okay to migrate after the hot plug is fully completed, but somewhere in the middle there are some problems and we need to clean up how to do that. Obviously we want libvirt to support the new interface. What we're doing in the short term is implementing the existing libvirt CPU hot plug interface in terms of the new API. That should be available reasonably soon. Peter Krempus, the person to talk to about that?
It's already pushed.
It's already pushed. Excellent. But that's a bit limited in what it can express. So in the longer term, we're looking at a new API and libvirt that allows us to fully exploit the QEMU interface. There's an SMP rework in progress, which just cleans up how we're parsing our SMP options and connecting with that. And at the moment, you can't unplug CPU 0 because that's a problem. There's various places in QEMU that assume if you have any CPUs, then you have a CPU 0, which is no longer potentially true with Hotplug. So it's not terribly hard to get rid of that. It's just a matter of dealing with it. And then there's boring legal stuff. Right, that's all. Sorry, we went a bit over time. Probably come to us individually for questions because we really are out of time now.